So welcome to the Deep Learning for Natural Language Processing course. Today's agenda is a bit shorter than usual for a couple of reasons. First, it's pretty much the remainings from the last class, and also we have a workshop that might take a bit of a time, so we might finish a couple of minutes early so you have some time to rest before we start the workshop, all right? So we'll talk a bit more about neural networks. We'll go over backpropagation. We'll revisit language models pretty much to give an introduction to neural language models, and then we'll start with recurrent neural networks and how we can apply them to change how we're doing language modeling. All right? So far, everything that we have been doing with neural nets and let's say how to calculate the gradients and backprop and everything, it's somehow theoretical. We saw, okay, we have to apply the chain rule after we get the final, let's say, prediction, and then we theoretically backprop that to all the nodes in our networks, and then we see how much we adjust, how fast, and so on. We'll see some practical examples how this actually takes place and what it means when you say, okay, how much I have to change my input and how does that affect my output. Hopefully it'll be also straightforward to do this. So as we were talking, so far we have been using neural networks to propagate the input signal forward through its parameters, weights and bias towards the moment of our decision. So we take all our inputs, we're going to multiply them by whatever weight we have. We're going to sum of this, put in our nonlinearity, plug this into a softmax, calculate whatever probability that we're trying to, let's say, investigate. Be that for figuring out what label a given context has, or let's say a sentiment and a sentence, and so on. But then the final decision, we pretty much, it's 0 or 1. So either the decision is correct or wrong, and we calculate how close we are from that decision, and based on that distance measure, we start updating all the parameters that we have in our neural network in an attempt to make our decisions and our weights, most importantly bias, closer to some meaningful representation. All right? Yeah, so during the process, the forward process, as we call it, we calculate the error associated with our guess and which direction we should move to improve ourselves. So how high the value or how low the value should be changed and how fast it should be changed through the learning rate. And then the idea is to use that error associated with whatever guess that we have, whatever prediction, and then we're going to take that error, all that calculation, and we're going to look back and readjust all the parameters that we have. Remember when we were talking about word to vec, what were our parameters? The vector of the center word, the context words, and whatever other free parameters that we had at that time. When we talk about the name-to-entity recognition, we scaled that to an actual multivariate problem in which we had several dimensions for all the words that we are composing in our context. But then I think the main question is here, how can we take the error that we associate with the incorrect answer and use that error to readjust the neural network's parameters in the direction of the last error in a way that how we can wiggle that value that initially is random to a way that it will produce less and less and less error. Hopefully it will be 0, but in fact it never is. We already did this, so how can we do this to begin with? Yes, we can. And we're going to use backprop to do this. This is also the idea of backpropagation comes from one of the 3 godfathers from AI, Hinton, Ian LeCun, and Yoshua Bengio. Later we'll see, this one is from Geoffrey Hinton, but we'll see how an idea from Yoshua was quite popular in the early days for doing neural language modeling, okay? We're pretty much just giving a name for something that we already did in the previous classes, and then hopefully we'll build on top of that, all right? So what is the main idea on backpropagation? The network makes a guess about a data using whatever parameters that we had. which is the word vectors or pre-trained word embeddings, biases, arbitrary weights that were initialized with whatever random distribution or uniform distribution or symmetric, it depends. And then we're going to measure that with our loss function, and then the error is backpropagated to adjust whatever wrong-headed parameters that we had. So pretty much we'll do what we have been doing the last classes, where we're going to take the derivatives and use that, and use the generalized chain rule in order to update all the weights that we have. Last class, we were updating the last layer, which we're calculating S with respect to bias, but then you're going to do this with respect to weights and all the other parameters that we have, all right? And this is kind of a spoiler. We will also reuse the derivatives computed for higher level layers to be used on the lower level ones. So since the higher level layers, there's pretty much the same in comparison with the low ones, there's no need for you to recompute that over again. If you're doing this by hand, which you should not to begin with, if you're redoing the same calculation over and over again, most likely there's something wrong, because you just need to do this once, and we'll see how that actually looks in practice, okay? So we will represent our neural network equation as a graph just to make it easier to visualize what we're going to do here. Our source nodes will be pretty much our inputs. Interior nodes are going to be our operations. We're going to use the same example that we had last class for named entity recognition. Later on, we'll see that we can apply this to different NLP tasks. It's pretty much the same idea. And then the edges will pass along the result of whatever operation that we have in our nodes. So we do have, well, where's the first one? Yeah, I think I'll put this later on. Yes, so we have our inputs right here. We're going to multiply that by whatever weight that we have. Then we'll sum that to a bias, and then we propagate that to whatever nonlinearity that we have, to a hidden layer, and then we have that hidden layer multiplied by another arbitrary weight that we have in the last part right here, and then we obtain this value, which we can input that into a softmax and decide, okay, whatever this value here, and we do this for all, let's say, for all the words that we have in our window as we move, what is a target word represented for us. In named entity recognition, if you remember correctly, we're trying to identify if that was a location, a person, or organization, but we can later, and we'll see later how we can expand this notion. So the idea that we have is, after we make our guess or we make our prediction, we want to go there and backpropagate our gradients in a way that we calculate the distance of whatever we calculate the distance between our prediction to the actual target that we have, and then we readjust, or we calculate how to readjust whatever the weights that we have here in our toy neural network. So if you remember, we start deriving S with respect to S, but then, if we want to calculate the derivative of S with respect to bias, if I remember correctly in the last class, we pretty much have to apply the chain rule and all the steps until we get to our bias right here. So, and there is something here in the between, but we'll talk about our local gradients. But for now, imagine that we calculate the derivative of our last stage right here, our S, then we apply the chain rule and start multiplying with the previous steps, in this case our hidden layer, with respect to H, and then with respect to Z, and then later on we'll get to the weight, or the gradient for the weight that we're interested. All right? This is pretty much what we do for backprop. There are some other details that we should take into consideration. So every time we're talking, we are calculating our downstream gradient, or the value that we are backpropagating here on, let's say, if we go from the end to the beginning to the output of this, and this from right to left direction, we have to consider whatever is coming from this downstream gradient, so in this case the upstream one, and of course we have also to take into account the local gradient, which is our nonlinearity in this case. So in order to calculate, let's say, the new values that we have in this case for z here, we have to take into consideration the upstream gradient, which is what is coming for the higher level layers, and also we take into consideration the adjustments that we have for our local gradient, or for our node right here. Okay? In this case, it's straightforward because we just have one input and output. What happens then, and in fact, that most of the case, we have multiple inputs there. So you have to take this into consideration as well when you're calculating your downstream gradient, and how that, oh yeah, of course. Oh yeah, and just this, if you remember last class, and I should get back to this a bit, remember that we saw when we were calculating the derivatives for higher levels, layers that we have in our neural network, we saw that some of them repeat it themselves. This is pretty much what's happening here. If we have a longer composition, we'll see that some of those, they will repeat again, so there is no need to recalculate it. But that being said, we just multiply both gradients right here, and then we obtain the downstream one, all right? So in this case right here, we do have multiple inputs, which means that eventually we're going to have to calculate a gradient for all of them. And of course, the internal node or the local gradient also has to be calculated with respect to each of those inputs. So on top of having to calculate the downstream for each of them, we also have to take into account the function that's combining them here and derive with respect to each and every one of them. So in this case right here, our upstream gradient will be multiplied by two different local ones when we take the derivative of z with respect to our weights, or our w, and then also the derivative of z with respect to our inputs, in our case here x. So, and then when we calculate the downstream, we'll see that we're receiving the same upstream gradient right here, but then when we get to this node, this multiplication node, we'll see that we have specific local gradients, right? And we'll see this later on the example. Imagine, I mean, we just saw two cases when we have one input and output. In this case, we have two inputs coming from this, this function, but it might be the case that this input right here is also used into another node, into another function. In this case, you have to consider both of whatever derivatives that you're calculating for that, all right? But we'll see a toy example on this. Oh, yeah, this is our downstream gradient. So let's take a look. I always get confused which side to look, but in any case. So let's see, we have here this toy neural network in which we have a function that's pretty much x plus y multiplied by the max of y and z right here. We have initial values for x, y, and z, and it doesn't matter what is the end value. In this case right here is 6, and we are using this to do whatever prediction, but we're interested, remember, and I've been repeating this quite a lot, that yes, we have this final value that we are, in this case, it's not actually a nonlinearity, but we have a nonlinearity that correlates input and output. But what it means, like, okay, I have to change my value by a decimal or by 2 points, and how does it actually affect from our input to our output? So if we take into account everything that we just saw right now, in a way that first we do the first pass, the forward pass, in which it's pretty much to execute the functions in the order of these nodes in this graph. So A, we're going to sum x and y, and then we have the value here for A, which is 3, and then we have the max between 2 and 0. We take 2 past that, multiply, we'll obtain 6, and now we have to see, okay, how can we adjust that? Since we're going to be using the local gradients for all of these guys right here, for all of these nodes, we can already calculate them. So if we calculate derivative of A with respect to x, we get 1 right here, this goes away, and we just have this. With y is the inverse. In this case, a with y, this goes away, x goes away, and we stay with y, and it's 1. When we do the derivative of the max here, b with respect to y is 1 for every time that y is greater than z, and in this case right here, it is. So we get ourselves y, which is, and we do the derivative of that, in this case is 1. If we consider the derivative of b with respect to z, it also will be 1 in case z is greater than y, but that's actually not our case. So in this case right here, the local gradient for z will be 0. Then if in the last one here is a times b, and that's straightforward. With respect to a, we get b, which is 2. And then with respect to b, we get a, which is 3 in this case. If you remember how we start to backpropagating things, the first element that we do the derivative of our last state right here, so f with respect to f in this case. And now we have to backprop all these values and all these alterations throughout the entire network. In this case, derivative of f with respect to f is 1. So now we have to calculate which values we're backpropping for each of those inputs in each stage of our network. So in this case right here, the the upstream gradient is 1 for both of them because they're coming from the same place. And then we multiply each of those inputs, A and B, with respect to their local gradients. So, and probably some of you already see some patterns on this, but we'll get to the takeaways on this. So to calculate the downstream gradient for A in this case right here is the upstream versus the local, multiplied by the local, so 1 times 2. So the new value on this here is 2. And for B, the new value here is 3 because we take the local gradient that we had, which was 3, and then 1 times 3 is 3. And then we continue doing this for all the other nodes that we have. In this case right here, we already use the new upstream that we have. So 3 will be multiplied by whatever local gradient that we have for this node max, which is our B. And we already saw that the local is 1 for y and 0 for x. And so 3 and 0 are the new values. And up there, we have the values of 2 and 2. And then, let's see, this case here. Yes. So, and this was pretty much what I was talking the last couple of slides. When we have 2 inputs right here for the same node, we have to do the local for all of them. But then when we have the same input used in different nodes in which we have different streams going through them, we have to make sure in the end to sum all these gradients in one. So the gradient that we have here for y is 5, and then in this case for x is 2, and for z is 0. And what this tells us, it tells us the following. It depends how much you change the value that you have for this input, they will grow accordingly, or they will reflect in your output according to this, let's say, magnitude. So if I take whatever value that I have here for x, and I change this value 0.1, most likely, not exactly, but since it's a simple one here, we'll see that whatever value that I'm changing, it will reflect in the same magnitude in my output. So let's say if I use here 1.1, the final value here, we're going to have 6.2. So whatever value that I put for x, it will double the value in our output in the end. And then if you want to play around, you can also do the same thing here for y. In this case, instead of using 2.1, you put 2.1, you see how much this here will affect in the end accordingly to whatever magnitude that we have. All right? Let's see if I forgot anything. I don't think so. Okay. Oh yeah. Takeaways. Depending on the nonlinearity, or in this case, the functions that we have, we'll see how that affects the flow that you have in your backprop. In this case right here, what we can see about what's happening with our upstream and downstream gradients. We see that first, the multiplication right here, we are altering whatever we have for the input stream. So in this case right here, we got 3 and 2, but when we calculate the backprop on that, we saw that those values, they changed, so they swap. The sum, in this case right here, took whatever you had for the upstream gradient and backprop to all its downstream ones. So since we got a 2 right here, you see that it replaced both of these inputs, in this case x and y, for whatever upstream that we had. And then in the max, what we have is it takes whatever upstream that you have and direct that magnitude to whatever value is the max in that function, in this, in this input. In this case right here, since the max is 2, whatever we are receiving, whatever we're receiving from our upstream gradient, it will be directed here in our downstream one. All right? Okay, now that we learn how to calculate that, and we did this for the sake of calculating the weights that we have for B, then we know that we have more parameters. So we have also to readjust, in this case, the weights that we have there. And now what we have to do? We have to calculate again the derivative of S with respect to S, and we start backpropping this until we reach our lower level layer, which in this case here is W. The thing is, up to this point right here in this addition for this case, we see that the higher level layers, they are pretty much the same. So there is no way, there is no need for you to recalculate that. You can simply reuse the values that you already calculated, so you don't reduplicate or duplicate the information that you're computing. Okay? Again, this is just to illustrate in practice, and we'll see this later on when we talk about LSTMs. We go even in details like, okay, this is a forget node, forget gate, input gate. This is to give you an idea what's happening behind the scenes. In practice, you change this for half of line of code and let the API do this for you. Unless, of course, you are working with architecture, optimization, then it's a bit different because you're going to be playing with this architectural details a bit more closely, all right? Yeah, so no need to duplicate these calculations over and over again. So what pretty much we're doing on the forward propagation, we visit the nodes in the topological order. So on every node, for every input that we have, we're simply doing the operations that we have there described. We're summing the inputs, we're multiplying, getting the max, and just going through in the forward direction. So we calculate the actual value for that node given whatever predecessor that we had there, all right? And then when we calculate the backprop here, we apply the chain rule to compute all the gradients, upstream one, local one, and downstream as well. We initialize our output gradient to 1, and from that we revisit all the nodes in the reverse order. And of course we compute all the gradients with respect to each node using its successor. So we are reusing, or we are using the values that we just recently recalculated. They are the new inputs, and we just do this back and forth. If we're doing this correctly, and if you're doing this by hand, again, don't do it. The complexity of doing this is the same because you're just doing the forward, again, pretty much the forward pass. And then we should go over some tips. I hope I cover most of the tips right now before we get to the workshop later on. On top of this, what we do have some regularization, in a way that before we would apply regularization to kind of prevent overfitting when we had a lot of features, but this was when it was initially proposed. Now, since we have a lot of parameters, it will overfit with respect to your training data. So the idea now that you use regularization, either you sum the absolute value of all the parameters that you have, or you sum the square value of all those parameters, is that you allow whatever architecture that you have and the weights that you have to generalize better for unseen examples. Also, a good sanity check, especially if you're working with large neural networks, you have a training set, we have training validation tests, you run your error analysis on the training, and if it is overfitting there, it's a good sign, because if you have that many parameters, most likely you will memorize what it has on the training side, right? Yes, this is good for this. Dropout. Since we have a lot of parameters, later on we'll see this, there's also a way for us to kind of prevent things to be dependent one from another. We don't want that specific inputs, they're completely, let's say, dependent on another one. Like, okay, if you alter one, let's say, input, it should also alter the value on the second one, and so on. We want to avoid that. And one way to avoid this is using dropout in a way that will simply turn off some inputs, some nodes, depending to 0. And then since you're batching this over your entire training, eventually you revisit all the training examples that you have. But when you are calculating their weights, probabilities, and gradients, you want to make sure that somehow not everything will be strictly connected with another. So how we do this at training time, we randomly set some of the inputs to each neural to 0 in a way that they have no influence or whatsoever when you're calculating, let's say, your prediction. You simply put them into 0. Because of that, on test time, you pretty much have to half the weights that you have, simply because now you have half of the training examples that you had before, except on the first layer. And by the way, these are probably, there's more, let's say, robust mathematical explanation for that, but a lot of these tips and rule of thumb that you have for neural networks, they are empirically tested. So, okay, how I do initialize the values of my weights, and which distribution do I use, how fast I change my learning rate, or the magnitude of my gradients. All of this, it kind of depends a lot on the problem that you have, and this is why you're going to find a bunch of different references for each case. Oh, you should use this optimizer or that, but it's just some general rule of thumb tip. This will, in practice, prevent the co-adaptation between features. And the reason for that, like, we don't want the feature only to be useful when another one exists. We want to prevent that from happening. I would say that the idea of using this, it's pretty much for you to have something between that all your features are independent and all your features are codependent. You want them to relate somehow, but not strictly like, okay, let's say in a logistic regression, or when they are totally independent when we're using naive Bayes. And let's see. Yeah, I guess that's it for dropout. Vectorization. Well, this, if you're using any modern API right now that I can remember, you're going to be forced to use matrix to do all of this, simply because they work in this tensor structure in a way that you'll be surprised how these things are optimized to work with matrix. Remember, in the very first example, when we saw word2vec, we did this using a mathematical notation, and we're not kind of using matrix, although matrix is a mathematical notation, but we're using actual formulas to do this. But later on, when we start talking about name change recognition, we saw how we calculate the Jacobians. We changed to matrix notation. There's a reason for that. Things get faster, like 1, 2, 3, 4 orders of magnitude faster if you use matrices and vectors. Also about nonlinearity, and this here should be in bold, and I think I mentioned this before, both the logistic regression and 10H, they are still used in various places when we want to get the probability. So in the end, when we are trying to calculate, okay, is this final value that I have, how probable is that to be a location in our previous class? Do we still use those two functions? However, When we have these inner layers, when we have those linearities in our hidden states, we don't use them anymore. We use other activation fonts, for example, ReLU, but this is, again, you'll see that depending on the architecture that you're using, this change here quite a lot. All right? And let me get this here. Parameter initialization. Normally, we'll initialize our weights to some small random value. We will avoid non-zero matrix simply because we don't want symmetry. We don't want our neural network to memorize everything, and this avoiding, not creating non-zero matrix, avoid our neural network to pretty much memorize everything. And how you actually initialize, how small or what is the value that you have to consider when you're initializing this through whatever random distribution that you have, random value from -r to +r. There's actually not exactly, okay, always do with this value. It's kind of a random one. The thing is, you want to choose a value that whatever weight you're initializing, they're not too high and too low, because this will make things harder to optimize later on. It will take a longer time. So usually it's a small range that you have. One way of doing this is to consider this Javier initialization that considers the input or the fan in the previous layer size that you have and the output or the next layer as well. Again, these are all more general tips, depending if you're on computer vision, NLP, I don't know, optimization, software engineering. It really depends on which is your area, okay? Optimizers. So how we should optimize the gradients that we have calculated so far. I was about to say in this class that yes, use add-on right here, that it pretty much, you adapt your optimizer to scale the parameter adjustments by an accumulated gradient. So it takes into account, let's say, the average of all the previous gradient that you have, or a weighted average and so on. And I would say always start with add-on optimizer. I think we didn't, yes, we provided this in the project description, how is the actual algorithm, but last week a new paper was published from Stanford, and they work with optimization. And they have this new one called Sophia. I wish I could give more details, but I still did not have time to read the paper. It was published on the 23rd of May. So if anyone makes a test in your projects, by the way, using this new one here, please let me know how that works. I'm quite curious. What else? Yeah, I mean, this is not an extensive list, how you change or how you adapt whatever, let's say, the magnitude of your gradients, but there's an extensive list. Adagrad, root, mean square, sparse atom, and what else? I don't remember. But in any case, learning rates. On top of how much you should change, how fast you change. And then on our learning rates, you can use a constant one. In this case, usually, by the way, the magnitude on how fast you do this in powers of 10. You can start with a specific value and stick with that throughout the entire training. What happens, well, before we talk on what happens in practice, if you have a learning rate that's too big, it might be the case that your step overshoots a global minimum, and you don't want that. And if it's too small, you're going to run, let's say, your optimization ever, and ever. For those that are already a bit familiar with this, we'll talk about how this reflects in the vanished gradient descent and exploding gradient descent, but it's pretty much because of this fellows right here also. And what happens in practice, and I think we mentioned this when we were talking about doc2vec. Remember when I said when we have to infer new vectors, there's kind of some parameters that we have to use, and among those parameters, I think it was a learning rate, initial learning rate, and some alpha. So what happened in practice is you start with a fixed value, and as you get better and better scores, this value will get smaller and smaller because probably you're approximating whatever function that you have closer to a global minimum, right? Well, you have all sort of techniques how to adjust this learning rate. You can use some of them, or you can do this by hand on a step like, I don't know, after a certain number of training epochs, I would simply decay my learning rate until I get a minimum. So if I get a minimum value, I know that I don't have to train this anymore, right? Yes, I think that should be enough for the workshop, and I hope I kept my promise to Dorothea to cover most of the topics before her talk. Now, we'll start taking a look on how we can use let's say, the architectures that we've seen so far in order to improve our language model. For that, we'll revisit language modeling briefly, simply because I want every lecture to be self-contained on itself when we publish it. But yeah, we'll get to neural language models in a minute. If you remember what is a language model, and remember that so later you don't get confused, okay, a language model is a recurrent neural network. No, they're completely different things. You can use one to obtain the other, but we'll put some reminders about this in the end, okay? So, language model is a system that assigns a probability to a piece of text. In this case, we have on Monday, the teacher saw all the students to open their. So what is the next word after that? Open their tomatoes, computers, exams, books. How do we know that some sentences make more sense than others? Simply because words that make sense, they have a higher probability to appear, given that you process enough text. And this idea, it gets stronger by the second. I mean, at the end of the class, I'll talk about some recent advance that we have in language modeling, but we'll get there. And how do we train a language model? Before or pre-deep learning, we learn the n-gram language model in a way that we consider theoretically all the previous states that we have. In practice, we see that this is actually not true, and how far our n-gram has to be in order for us to make a good prediction. A unigram, and if you remember, all the words are kind of independent. Bigrams, in which we visit every 2 words at a time. Oops, sorry for that. Trigrams, fourgrams, and so on and so forth. Okay? So pretty much we are collecting the statistics about how frequent those different n-grams are and how we can use this to predict our next word. So pretty much we calculate what is the probability of the next one, taking into account the entire context. When I say entire, really between quotes right here, we know that we cannot look through the entire corpus that we have. Yes, so we saw that there is no need for us to take this into consideration, and we can use some assumptions for that in a way that, if you remember our lecture 3, if I'm not wrong, we talk about how it's not necessary for you to look to the entire, let's say, past state that you have. You just need to look a little bit, and whatever n states that you have, and you'll be fine. The thing is, this is actually not true. We'll see, we told a kind of a lie in the beginning to kind of motivate things. There is some problems, and just looking a little bit behind, you want to look as much as you can, but you have to do this in a smart way because you don't want to keep track of everything from the past, but in any case, we'll get there. So we saw that using the Markov assumption, we just have to pretty much, in this case here, look to, this is a trigram if we look to the denominator, but it's a fourgram if you consider that all the words in the context window that you have, but in any case, what is the probability of a new word right here, given that we have students open there? So we have to count how many times the entire foreground sentence appeared and divide by whatever context that we have. And if you're lucky enough and your data shows that, you're going to be able to calculate the probability of this unseen word. So in case you have, considering that the context appeared just 1,000 times and books appear 400 times, you have 40% of the next word here being books and 10% the word being exams if it occur only 100 times in this specific corpus slash example. Oh yeah, we don't need to look to the entire thing, just a little bit ahead. However, we do have some issues when we're taking this into consideration. And one of them, we learn how to deal, if you remember, smoothing, back off, stupid back off, and so on. If students open their whatever W we have here never occur in your data, so let's say books or exams never occur, what's going to happen? Then the probability of this sequence to appear is 0. And we don't want that, so how we deal with this? We can do smoothing. So we add 1 to every single example that does not belong to our training data. What if student open there, which is our context without the word appear there? If that never occurs in our training data, how we can handle this? Well, you can do some back off and hopefully it will be fine. And then if you need to store the count of all the anagrams that you saw in your corpus, what do? You buy more disks. Probably that's not the best solution to handle this. And this is something that we actually didn't talk at that time when we talk about statistical language modeling. There's just so much, or it's just how far you can grow. There is a upper bound to that. Theoretically, they're great. In practice, yeah, kind of-ish. And I'll show you an example. Let's say we consider this trigram language model, and we have today the price of gold per ton, while production of shoe lasts and shoe industry. The bank intervened just after it considered and rejected IMF demand to rebuild depleted European stocks, September 30, and primary 76 cents a share. Awesome text. All the words are correct, but grammatically it's gibberish. And this happens a lot with those. Not to mention, there's no way to improve that once you have trained. You have to retrain the entire model again because maybe you have new words. So this makes things not very easy to scale and generalize. So we need a way for us to consider, let's say, more than 3, 4, or 5 words. The initial work that we're going to see kind of handle this, and people still today, they try to make this input larger and larger, but we'll talk about this probably in around an hour or so. So there are some limitations, as we saw, for statistical language modeling that's quite hard to overcome. What we learned so far that we can apply that to, let's say, have a larger context or to have a way that all the words they do relate in a specific order in our input. We already saw that in empty-entity recognition. How can we expand that notion of thinking about a label for a specific word in a context? How can we use that to instead calculate a new word in our sequence, take into account that context window into consideration? So just as a reminder, remember when we were talking about this task, our name-entity recognition task, we had a context window right here. In this context window, we were concatenating all the input vectors, multiplying by whatever weight. We put this into nonlinearity, multiply by another weight right here, and then we have one final value that we can plug into a softmax and say, hey, that middle word right here does belong to a location. How can we use that same idea and move this? Instead of providing a label, we provide another word. So instead of classifying with respect to a handful of labels, I use my entire vocabulary and then I can say, hey, the label of the word is the word itself. So it's kind of an unsupervised learning if you look in this direction, since you don't have a label for the word, but the word themselves are a label. All right? So how can we change that to our problem right now, and we move from this statistical language model to this neural one? By the way, this was, and when I mentioned the three godfathers from AI, this was proposed in around, I think, 2003 by Yoshua Bengio, but was using some work previously from the year 2000. But later on, we see how this has some limitations, and people come up with ways to improve this model. So what is the idea? Now we still have our context window. In this case right here, it's just 4 words, but think that you can have as many words as you want in this sliding window. Then we concatenate these word embeddings into this representation, and then we multiply those concatenating embeddings with multiply them by some weight, plug in some bias, put that into a function, our nonlinearity. Then we take whatever hidden layer, hidden state that we had, multiply by a different weight, again, use different bias, and by the way, everything that we learned before, how to calculate how much we have to change those weights that we have, it goes the same way. We won't go over in details how it works. Well, that's not entirely true. We do a bit more details when we talk about vanishing gradients, but we'll be more on a higher level. But in any case, after we calculate the value here to do our prediction, we can put this into a nonlinearity and make this value to indicate to us what is the next word, or what is the word that would make more sense taking into account this context. Hopefully, if we have, let's say, enough data, we'll see that words that make sense, they should have the higher probability. Of course, this also depends on the data that you're training and so on. This is why you see that more and more those large language models, they use a ridiculous amount of text to simply calculate language models. There is a benefit on that. Hopefully, when we talk about pre-training, transfer learning, we'll be able to advocate this a bit more. The bunny version is by taking into consideration this context that we have. It's a bit different than this architecture. We'll see the new one. You get a grasp on the language, a good grasp. And the more parameters that you have, more implicit relationships you can capture by these parameters, and you can transfer this to different tasks. But in any case, we'll get there. So, take into consideration this setup, it's pretty much the same setup we have for name-to-entity recognition, but now we are providing a prediction for the next word. We did have some improvements. So we take care of the sparsity problem. We don't need to store all observed n-grams, since we have this context window and we change the weights for every single of those words. However, we still have some remaining problems in a way that the fixed window right here is too small. In this architecture, we are considering 4, and we can grow up to, I don't know how many n words, but still, it doesn't take into account a longer context, and that can be a problem for us. Also, enlarging this window enlarges our weight. Window cannot be large enough, of course, and the words are multiplied by completely different weights as we move along, so we don't take right now into consideration the actual previous states to influence the new words. So we want to hopefully want to avoid that. And there is no symmetry in how the inputs are processed as well. Now, let's try to change this a bit in a way that we can reuse stuff that we're already calculating in order to make a better prediction, in a way that you want to avoid this problem that every single word is multiplied by a different weight. Instead, we want that this word, the next one, let's say considering state t plus 1, taking into consideration whatever it learned from the previous state, and we can do this interactively. So what is the main idea with this? We have an input sequence right here. We still have our hidden states, but then our weight matrix right here, we're going to reuse, let's say, we're going to take the prediction that we have used for one word right here into the next, and then we're going to reuse the weight that we calculated in the previous hidden state to the new one. And then we're going to reuse the same weight over and over again in an attempt that we're going to be able to make this weight better and better. There is some detail, maybe I'll jump ahead. At training state, we don't need to actually use the final prediction that we have. We can simply use the actual words. And test is a bit different because imagine that for every word we do remember, if you remember the previous slide, for every hidden state, we're going to calculate a given probability, a given prediction, and that this will be the next word. A training step, we just simply go there and use the words that we already have. But in any case, we will get there. So the idea is, given whatever sequence that we have, and we're going to reuse these weights over and over again, the moment that I want to predict a new word that's whatever, it's not in this sequence, I can use that prediction, which hopefully will take into account all the previous states, and I can use that to see, okay, what is the next word right here? Of course, if this is in training step, we know exactly how it is, so we can calculate the distance between that. But if it's in test or in inference time, we can simply use that probability and say, hey, the next word is books, or the next word is exams, all right? Oops, yes, okay. So the idea of recurrent neural networks and the name recurrent comes because we are reusing those weights over and over again. It's because it remembers the past to some extent, and maybe I should have put this in quotes. It remembers the past to some extent, because there are some problems associated with that as well. And the decisions that we have here, of course, decisions are influenced by what it has learned from the past. So all the weights that we're using, we're going to be reusing them for later states. So we don't have the problem that now all the words are independent. Much on the contrary, one word is affecting the prediction for the other. All right? Yeah, the hidden state will capture the possible relationships that we have between those consecutive words in a serial and ordered manner. And for those that already are familiar with this kind of architecture, say, haha, that's a problem. Yes, it is a problem because you have to do things in a serial manner. So you cannot paralyze that. Later on, when we get to other architectures, you see that there is a way to cope with that. If we change the architecture a bit, you can pretty much look at the entire sequence at the same time. And this was quite revolutionary, I would say. But keep in mind that we're right now around 2004, 2005. We'll get to 2019, about 3 or 4 classes, all right? Yeah, their sharing parameters can be effective to leverage the relationship between one input item and its surrounding neighbors. And we'll see how that sharing can be a problem if the sequence is too long. But let's stick on the theoretical here. This does capture all the relationships within our words, all right? And so how this will look like now. We'll still have our context window. Again, this can be a bit larger. And we have our words as input vectors, as one-hot vectors, which we can relate or not with some sort of embeddings, pre-trained or randomly initialized. And I hopefully put this. So yeah, we will multiply whatever input that we have for against whatever weight to represent those words. And this weights right here, they can be pre-trained, and you can say, well, since I have this entire architecture in which we're optimizing the whole thing, why do I use pre-trained word embeddings? Simply because the gap that you have to move from a random initialized weight to something that was already optimized for a given language is way smaller than if you start from scratch. And this is the same for modern architectures. In modern NLP, pretty much you always have, this is a huge spoiler by the way, you always have a base task, and this base task you capture, let's say, general features from your language, and then on top of that you start building on more specific things. Now looking at 2023, you see that also debatable if this we call fine-tuning or this optimization for specific tasks does true help, or if you have a good understanding of ground and basic knowledge of the language, that's enough for whatever task you have. In case you're more interested on this, you can talk with me afterwards. There's some papers that were published within the last month. They are refuting this idea, but coming back to this, and I should stop deviating that much. So after we have our input sequence right here, we have our hidden layers in a way that, remember, we want to make sure that for every new word that I have in this sequence, I'm going to use a previous hidden state to calculate, recalculate, or to, let's say, carry on the influence of that hidden state, previous hidden state, to a new one. And you might ask, okay, but where this hidden state 0 right here is coming from? Usually you initialize this as a 0, so in the very first step, this first one here is non-existent, this part right here, or you randomly initialize them with one number. Later on, you optimize the whole thing from end to end, so it really doesn't matter that much. And then, after we calculate this hidden state right here, which takes into account the previous one, take into account our words and our input, the weight associated with that input, and some bias. We put that, again, in the softmax, but instead of considering the entire context, we consider one word and already use that prediction to calculate the new one. And we do this over and over again until we reach our last step. Oh yeah, this I already said that you can use some pre-trained word embeddings for this. And just to make some connection with previous class, can I use pre-trained word embeddings, let's say from Word2Vec, from Glove, or FastText to do this? Yes, you can. So this was actually done, I don't know, from 2013 until 2017. This was done extensively. And actually really cool way for you to kind of optimize the weights that you have from those techniques. Remember, when we're calculating the weights from Word2Vec and Glove, it's kind of a static. But if you plug this into this architecture, you can continue really between quotes here the training for those weights, right? Yes, so in each state, as we're talking about, you do have on every word, you have the prediction that you can either use as an input for the next word. Of course, this will happen most likely on inference time, and training time. You can pretty much just, you calculate the distance, by the way, I didn't emphasize that. You calculate the error for that, but in the end, you actually use the word that you have. There's no need to use whatever prediction that you have in your training. You just use the prediction to calculate, readjust the weights that you have. And hopefully you can already see how some problems can arise from this. If you have a bad probability distribution, most likely for every new step, you're going to be predicting words that do not relate with that sequence. And this is one of the reasons some models, they do have these hallucinations in the way that you start writing something, and yes, the first 1, 2, 3, 4 words make a lot of sense, and if you extend that, things just get out of hand, right? Oh yeah, advantages and disadvantages. So we can process any length input, and this is kind of good and bad in a way. The computation for a step T can, in theory, use the information for many steps back. This is awesome. It carries out a problem, but we'll talk about this problem in next class. The model size does not increase for the longer input, because at inference time, and also in training time, you're doing this one step at a time. And the most important thing is that the same weights are being applied as we talked before, over and over again. So now we don't have any more independent weights. Some disadvantages for that. Recurrent computation is slow, simply because you have to revisit one word at a time to make the new prediction. So there is no way for you to parallelize this with this architecture. Later on, we'll see, especially when you get to transformers, how you can parallelize this. There's also another problem transforming with self-attention. It grows also quadratically, but it's like this. Every new solution carries out a bunch of different problems, and then people start working on those problems, but in any case, it is a good thing. In practice, it is difficult to access the information from many steps back. And what we mean by that is the longer is your sequence, it keeps getting harder and harder to remember things. Simply because when we do the backprop on this, we have to multiply all the gradients, and what we learn about when we have to multiply things. Either the values will get vanishing smaller or they will grow exponentially. So this can be an issue. And also later we'll see that, let's say, higher level hidden layers, they have little influence if you compare with lower level ones when we're backpropping, and that's a huge problem, all right? So how do we train RNN language model, or RNN-LM for short? We get a big corpus of text, which is a sequence of words from 1 to T, and then we feed this into a recurrent neural network and compute the output distribution or our prediction for every step that we have, or for every word. And then we predict the probability distribution of every word given the words so far. So pretty much we're just doing language modeling over and over again, but now with this new architecture, right? The loss function on each step is the cross entropy between the predict probability, or our prediction right here, and the true word that we know what it is, at least on training time. And then on average, you can average all the losses that you have in whatever sequence that you have, or you can sum to have a grasp on how much your model deteriorates on every step, depending on what kind of error analysis that you're doing. Okay? So just as a recap, and by the way, I hope you're seeing how we're building the blocks from the first time we did a derivative for word to vec, and we were calculating that probability, and then we moved to multivariate. Now we're on recurrent neural network, and this will scale to how we address some problems in recurrent neural networks. And then we move to LSTMs, gated recurrent units, and then we have a pause to talk about CNNs if we have time. If not, I will provide a very short video on this, but then we'll see more interesting stuff later. So how we do this, we have our corpus, our input vectors will multiply by whatever embeddings that we have, pre-trained or not. Then for each step, we calculate probability distribution for the most probable word that we have. We calculate our loss, we adjust that, or we use the actual prediction to infer new words back and forth. Yeah, we already talked about how to calculate the average loss for the entire sequence, so we can move on. So computing optimization for training recurrent neural network language model. So computing the loss and gradients across the entire corpus is too expensive. It's the same problem that we had before. We don't do this for the entire corpus, we do this in batches. In practice, we consider what it means. This in batch is simply a sentence or half sentence or a paragraph, depending how much, let's say, robust you want your model to be and how much computing power you have, of course. And we already talked about this. The stochastic gradient descent allows us to compute a loss and gradients for a small chunk. So not for the entire thing in update, but for small pieces of text, and we update accordingly to this specific chunk that we have. And we do this for the entire corpus, and hopefully at the end you're going to have all, let's say, within your parameters, a good representation for what you have in your corpus. And then you keep doing this until you reach the end. And then how we actually do this alteration in the gradient that we have, how we update those values. We simply backprop through the entire network. So when we're moving forward on this structure, on this architecture, we're propagating here the weights from each hidden state to another until we do the final prediction, not the final prediction, for the next prediction. But then after that, we have to start pretty much updating the values from our entire architecture. How we do this? We simply backprop through the entire network over and over again. And you can pretty much relate with that. It's exactly the same thing we did for those three nodes in your network that we had with max, multiplication, and addition. But now we have, let's say, more arbitrary weights. We have some nonlinear functions there, but essentially it's pretty much the same, okay? So how we calculate the gradient for this first or last, it depends in which direction you're looking to this. You pretty much start, I thought I had the entire sequence here. You pretty much calculate the gradient from all the upper strings until we get, or the upper higher level layers until we get to this one. So it's for the entire sequence. Okie dokie. So how do we evaluate a neural language model? How do we know if this model is a good or bad one? We already learned how to do this. It's the same idea as before. We calculate the perplexity on this model. So we can go forward in this. So perplexity is the inverse probability of the test set normalized by the number of words. And if you remember correctly, the lower the perplexity, the lower is the surprise that you have of whatever new words that you're predicting, the better is. If you have a higher perplexity, a higher degree of, let's say, surprise or entropy in this case, it means that your model is probably not a good one. But yes, we already saw this. Yeah, I think I spoiled this. So why should we do this, let's say, new approach of calculating a language model or coming up with a language model, since we already knew how to do this? Simply because it makes things better. It does capture more details in whatever language that you have. So imagine that before this model was, let's say, proposed, if you're using interpolated answer knee, and I think I put a slide on this on lecture 2 or 3, I don't remember. When you're calculating the perplexity of your language model using all the backoff and smoothing techniques that we had, you would come up with a perplexity around 70%. And when this idea, okay, it's a LSTM in this case, so it's not actually a fair comparison, but LSTM is simply fancy RNNs. We drop like 40 points on that, 30 points on that. So it does improve things quite a lot, okay? So probably you're already seeing that things start to change, and I guess on every class now we'll see that, yes, but there's this new architecture, but there's this new architecture, and now there's this new one. And things change quite fast, especially in NLP land, now that NLP land is pretty much neural network land. So do RNNs, do they solve all of our problems? Can we apply RNNs to every single task that we have? Well, you sure can apply, but they do not solve. There's some really huge drawbacks on that. The serial analysis is one problem. The longer your sequence, the less you're going to remember your past states. This is also a problem. But they did change things forever in a way that now, honestly, I cannot think about one NLP task that would not benefit from having a robust language model. If you have a good knowledge on whatever language you have, it does carry out to other tasks. And this is possible because we were able to scale that because of this architecture in this sense. Oh yeah, do not get attached things. We'll see that this here will change probably in the next slide already or the next class. Yes, language model is a benchmark task that helps us measure our progress on understanding the language. And you will see that the use of pre-trained language models or pre-trained large language models, it kind of touches every single task in NLP. If you're doing from named entity recognition to, let's say, utterance analysis in chat dialogue systems, you see that the base of that, it's either a pre-trained language model or you're building your own language model from scratch. So some examples, you can use this in predictive typing. This is pretty much language model 101, speech recognition, handwriting recognition, grammar, spelling correction. Machine translation, we'll see that later on. We're going to use the same idea of concatenating hidden states, and then instead of predicting a new word from the same language, by just inserting one given token, and if you have some aligned text, you can generalize to transform one signal to another completely different one. And I'm using signal on purpose because when we talk about machine translation, usually what we think, oh yeah, English to French, German to English. But machine translation is way more than this. You can, let's say, codes, one code from C to Python, natural text to, I don't know, Haskell. No, not Haskell. Haskell is complicated. But in any case, text summarization, which it depends on which text summarization area you are, sub-area. It can be seen as a summary machine translation problem because you're translating one large text into a smaller one, so it's translation from the same language. Of course, that falls true if you have, let's say, multi-document, multi-source, abstractive summarization, then things get a little bit more complicated. Dialogue systems and so on. Language model is the fundamental building block on any NLP task you have. Let's see if this changes in the future. So far, I mean, until now, this is pretty much the standard. Okay. Yeah, I promise we'll finish a bit early. It might be just 2 minutes early, I'm sorry. So how can we use the architecture that we had before and extrapolate this for other tasks? So we remember when we were calculating, when we were propagating the weights from previous hidden states to other, I talk about, say, yeah, we do some predictions right here. So why not to use that prediction for something different than the actual word? Let's say we want to do part of speech tagging. Since my weights are capturing the previous one, maybe it will also capture the relationship between part of speech tags. And then the prediction here, instead of calculating the distance between the next word, I can simply calculate the distance from the actual label that I have for that word. Also, we can apply the exact same sequence and use that to see if, let's say, this sentence, the movie was amazingly abysmal, is a good sentence or is a good or a bad sentence, well, negative sentence or positive. For those that already know bidirectional models, you can say, ha, this example here sucks because the last word here is a bad word. So when we read the entire thing, it will change the entire meaning. Yes, that's very much true. But when we get to bi-LSTMs, we'll see that how we can look at context on both sides and cope with this one-directional problem, right? Well, you can use the last state to categorize a sentence as positive or negative, or we can use the signals from each and every prediction and input this as an extra weight to whatever representation that we have on the sentence to make a better, let's say, a better assessment or a better classification. Also, we can use this for question and answering. Of course, question and answering has something different because depending on the task, you might be using context or not, in a way that we can use the same sentence representation in whatever context that we have to predict our answer. And all of them, they're using exactly the same, between quotes here, between the same structure, the same architecture. In practice, we'll see that things are a bit different. Oh yeah, machine translation, we'll see that later on when we talk about this architecture, this sequence to sequence, in a way that we're going to have something encoding a given sentence and then decoding that sentence with whatever target that we have. We see it uses pretty much two RNNs. In this case, here we're saying eu gosto de batatas, and then we have end of sentence token, and I know that when I process this, it means that my target sentence is coming. So my prediction there, it should be towards that, and since and this is pretty much language model over again. We have an initial hidden state that now we don't initialize as zeros. We now have an entire history calculated, and then for every prediction, for every new word, we fit into a system and we start generating this over again. Again, a spoiler, on the next class you can say, well, how do you guarantee that this here is a good representation for the entire thing? You don't. There are ways to kind of relate your past with your future on specific timestamps, but we'll talk about this when we visit attention, right? And I should not spoil that many classes ahead. Yeah. Major takeaway, language model is a system that predicts the next word, so it's a representation of our language. Whatever that representation is, those parameters, those ways, they are capturing that. And when we talk about recurrent neural network, is a big family of neural networks. We saw the base one, we have then, we'll talk about LSTMs, gated recurrent units, and so on. In which we take a sequential input of any length, we apply the same weights on each step, and hopefully this will be carry on as we progress. And we can optionally produce an output on each step, or we can, as we saw, we use the prediction to, let's say, instead of new word, I come up with a tag or sentiment or whatever. And recurrent neural network is not language model. So remember that, it's probably on the exam, okay? So I guess that's it for today. Yes.